Hello everyone. Today we are going to discuss combined one-dimensional heat conduction equation. This is unit number 1 and lecture number 5, and our course is heat and mass transfer. So uh, if we look at the one-dimensional transient heat conduction equation for the plane wall, for the cylinder, for sphere, we see that all three equation can be combined together, okay, and they can be expressed in a compact form, as we can see through this equation, okay, that is 1 upon r to the power n del over del r into r to the power n k del t over del r plus uh, uh, E generation. Here E generation is basically heat generation per unit volume, okay, heat generation per unit volume, and then and that is equal to rho c del t over rho c or del t over del t, okay. This capital T represents the temperature, change in temperature, and this small delta t represents the time, okay, the time for which a phenomena was observed, or you can say the change of time, okay. So in this equation, this equation is basically a combined one-dimensional heat conduction equation, okay. So in this equation, if we put n equal to 0 for a plane wall, what we get, we will get a heat conduction equation for the one-dimensional plane wall, okay, that the one that we derived earlier. Then if we put n equal to 1, then this equation will be will be converted into a general heat conduction equation for a cylinder. Then again, if we put n equal to 2, then this equation will be applicable to the sphere for a one dimensional for one dimensional heat conduction, okay. So in the case of plane wall, it is customary to replace variable r by x, okay. So when we are talking in terms of r, we will replace r by x. This equation can be simplified by for steady or no heat generation equation, as we have earlier discussed. So there are some examples, okay. We will be first going through some examples related to the heat conduction, okay. So the first example that we are looking here at is heat conduction through the bottom of a pan, okay. So this is a pan through the and through this pan we will look what is how the heat conduction takes place and how much heat conduction takes place, okay. So consider a pan steel on a electric range to cook spaghetti, and this example I have taken from the heat and mass transfer by Sanjil, okay. So you can, if you have this book, you can go through this example from the book itself, okay. So the bottom section of the pan is L equal to 0.4 centimeter thick and has a diameter of this 18 centimeter. The electric heating unit on the range of uh, range consumes 800 watt power during cooking, and 80% of the heat generated in heating element is transferred uniformly to the pan, okay. So whatever heat is generated out of 800 watt, 80% of the heat is directly transferred or uniformly transferred to the pan, okay. Assume constant thermal conductivity, obtain the differential equation that describes the variation of temperature in the bottom section of the pan during the steady equation, okay. So this is the problem that we have to that we have to go through, and we will see how the problem is being solved, okay. So again, this problem is self-explanatory, that the bottom section of the pan has a large surface area relative to its thickness and can be approximated as a large plane wall, okay. Why we are approximating it as a large plane wall? Because the surface area is large compared to its thickness, okay. Because of this reason, we are considering it as a large plane wall, and heat flux is applied to the bottom surface of pan uniformly, and the condition on the inner surface are also uniform. Therefore, we expect the heat transfer through the bottom section of pan to be from the bottom surface towards the top, and heat transfer of in this case can be reasonably approximated as being one dimensional, taking the direction of normal to the bottom surface of the pan to be uh, along x-axis. So will get T equal to Tx during steady state operation, since the temperature in this case will depend only on one direction, and let's say that direction is x direction. So the thermal conductivity is given to be constant. There is no heat generation in the medium within the bottom section of the pan. Therefore, the differential equation governing the rate of variation of temperature in the bottom section of the pan in this case is simply. So as we can see that the temperature difference the differential equation governing the variation of temperature in the bottom section of the pan in this case can be simplified as like this del 2t over del x square equal to 0. That is also called the Laplace equation, which is a steady one dimensional heat conduction equation in rectangular coordinate under the condition of constant thermal conductivity and no heat generation. Okay, so uh, 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 we can solve this problem by simply integrating this equation. Then here this is another problem, that heat conduction in a resistance heater, that here there is a resistance heater and we want to know how much heat is being generated because of this heater, and what is the effect of this heat generation on heat transfer. Okay, so this is the capacity of resistance heater, which is 2 kilowatt, 2 kilowatt, and the thermal conductivity is 15 watt per meter per degree Celsius, and the diameter is given as 0.4 centimeter, and length is given as 50 centimeter. We have to calculate the uh, uh, I mean we have to calculate the amount of heat generated. Okay, so assume the variation of thermal conductivity of the wire or temperature to be negligible. Obtain the we will obtain the thermal equation that describes the variation of temperature in the wire during steady state operation. Okay, so this is the heat generated by the wire, as we have also was solved one problem earlier. So this is how we will get the heat generated per unit volume. So this is the wattage or power of the heater, which is 2000 watt, and this represents the surface area of the wire. Okay, heating wire. So we get this this is the amount of heat generated per unit volume, or heat generation by the heater. Okay, so thermal conductivity, as we know that it is given to be constant. So the differential equation that governs the variation of temperature in the wire is simply can be simplified in this way. Okay, again you can see this is the general heat conduction equation for a case of cylinder. Okay, so and for the cylindrical case, the equation is 1 upon r d over dr into r dt over dr plus heat generation upon heat generated per unit volume divided by the thermal conductivity, that is equal to 0. Here 0 has come because we are considering the steady state condition. Okay, so the solution of this equation will give us uh, uh, you can say temperature variation with respect to the space. Then again the cooling of hot metal ball in the air. Okay, so this is the ball which is at 600 degree Fahrenheit initially, and ambient temperature is 70 degree Fahrenheit, 75 Fahrenheit. So the heat will be transferred from the higher from the metal ball to the atmosphere. Okay, so again we can solve this equation by utilizing the since the body is spherical, so uh, we will utilize the heat conduction equation, general heat conduction equation for the sphere. Okay, and in this case, since heat generation is 0, so heat generation, the term of heat generation will be eliminated, and only these two terms, the temperature variation with respect to the time and temperature variation across the radius of the sphere, or all, we can say the ball, will be taken into account. Okay, so this is how this equation is for the spherical system will be transformed, and the solution of this equation will give us the other parameter that are required to understand the temperature variation uh, across the radius as well as with time. So, general conduction equation, as we discussed, that assumes that, especially in case of one-dimensional heat conduction equation, we assume that heat conduction in other direction is negligible. Most heat transfer problem encountered in practice can be approximated as being one-dimensional, and we mostly deal with such problem only in this context. However, this is not always the case. Sometimes we need to consider the heat transfer in other direction as well. So such heat conduction problem can be said to be multidimensional, and we will try to develop further the governing differential equation for such system in rectangular, cylindrical and spherical coordinate. Till now we have only obtained the general heat conduction equation in one direction only. Okay, but the heat transfer phenomena is a complex phenomena, and uh, we have to find out the general equation for rectangular coordinate, cylindrical coordinate and spherical coordinate in all direction, as well as with respect to the time. Okay, so uh, we will move in that direction. So if we consider this, let us consider this three-dimensional object. You can say this is a rectangular object, consist of rectangular, or you can say the cubical uh, object, and we will consider the heat transfer as well as heat generation, as well as the rate of heat change of content of the element. Okay, so as we have earlier derived for one dimensional equation, again we will consider the rate of heat conduction at x, y and z. In case of one dimensional heat conduction equation, we have considered only heat conduction at x direction only. Okay, now the heat conduction rate of heat conduction at x, y and z direction, and rate of heat conduction at x plus delta x, y plus delta y and z plus z direction, as we can see from this element. Okay, and plus the rate of heat generation inside the element, that will balance the rate of change of energy content of the element. Okay, so this is basically the conservation of energy equation. Okay, so heat which is entering at x, y and z, heat which is conducted through x, y and z surface, then heat conducted through x plus delta x, y plus delta y plus z plus delta z, and the rate of heat generation inside the element, mm, all will contribute to the change of the internal energy content of the element that we are considering here. So this is the equation that we will get, that heat conducted through x will be we can term it as q dot x, then q dot y will represent the conducted through along y direction, then qz along the z direction, and these other parameters like q x plus delta x, y plus delta y and q z plus delta z will represent the uh, heat conducted through x plus delta x, y plus delta y and z plus delta z, and this represents the E element represents the heat generated within this element, that is equal to delta E of the element and divided by the time, change in the energy content of the element divided by the time. Okay, because we are considering when we are considering the rates only. Okay, so that is why the change in the energy content of the element will be also represented in terms of rate. Okay, So as we know that delta x, delta y and delta z is nothing but the volume of the element, and change in the energy content of the element and the rate of heat generated within the element can be expressed as you can see from these two equations, delta E of the element equal to delta T plus delta T minus Et, that is equal to mc into this capital T represents the temperature, so the T after time t plus delta T, and T represents the temperature at time t, so that is equal to rho c delta x delta y delta z, which is actually the volume, into t plus delta T minus tt. Okay, so the total you can say the heat generated within the element is equal to E generation into volume. Okay, small e gen means the energy heat generated per unit volume. Okay, so if we multiply this with the volume of the element, we will get the total heat generated within the volume. So that is equal to E gen or delta x delta y into delta z. So this derivation is similar to the derivation that we have earlier did for one-dimensional heat conduction. Only thing is that this time other two heat transfer through other two direction we have considered, heat conduction through other two direction x, y and z we have considered. That is why it has become a little bit complicated, but the concept that we utilized earlier remains the same. Okay, so putting all these values in this equation, we get this equation. Okay, and if we divide by this equation by delta x delta y delta z, this equation will transform into this form. Okay, q q x plus delta x minus q dot x divided by delta x, and keep this element outside this term. Okay, in the similar fashion, we can also do the same thing for y and y plus delta y, and keep this term out of this bracket. Similarly, same thing can be done along z-axis. Okay, and that is equal to egen. Again, you can see that this delta x delta y delta z term is not here, because after dividing this by delta x delta y delta z, this term has become unity. So that is equal to again rho c, because we have divided by delta x delta y delta z, so this has become, this term as we can see has come over here. Okay, so the delta x delta y delta z term is eliminated from here and from here. So further, if we further simplify this equation, what we get, that ax represents the area along x-axis. So area along x-axis is represented along I mean ax represents the area through which x-axis passes, or which is cut ax represents the area through which x-axis cut perpendicularly. Okay, so which is given by delta y delta z. Ay represents is equal to delta x into delta z. Okay, similarly az represents the area through which z axis cut, or you can say the area through which the z-axis makes a 90-degree angle. Okay, so az equal to delta x into delta y. So by putting all these values and taking the limits as delta x delta y delta z and delta t tending to 0, we will get this kind of equation. Okay, del over del x into k del t over del x plus del over del y k del t over del y plus del over del z k del t over del z, and plus heat generation, that is equal to rho c del over del t over del t. Okay, so this is the equation. Here you can see that k is inside this bracket. Okay, it means that this equation that we have derived here actually represents the general form of the equation. Okay, and since thermal conductivity also depends upon many factors, so that is why it is put inside the bracket. Okay, in case when we assume that the heat thermal conductivity is constant or uniform only in in that particular case, this K will come out from the bracket. So this is the thing that we have done here. After taking limit, we have taken limit q del over del x minus qx upon delta x into 1 upon y into delta z. So after taking limit, we can write this as equation. Actually, this is how this term has arrived. Okay, so 1 upon delta y into delta x. So further, after putting this qx represents the rate of heat transfer along x-axis, so which is given by the Fourier's equation, that is equal to minus k into a is the area along x-axis, so delta y into delta z upon del t over del x. So again you can see that this delta y delta z and this delta y delta z gets cancelled here, okay, from each other, and that is why we got this we got this equation. Okay, similarly along y-axis we get this, and along z-axis we got this. Okay, and this is what and all these terms are substituted over here. So if we consider thermal conductivity to be constant, then what we get, we this K will come out of this bracket. Okay, so what will happen, that this term will become del 2t over del x square, as you can see here. Then del 2t over del y square, del 2t over del z square, and K, after dividing this equation by K, we will get this Egen upon K, and then this term 1 upon alpha del T over del T, where alpha is the thermal diffusivity, as we have earlier discussed, that is equal to K upon rho Cp. So as you can see here, it is also written alpha equal to K upon rho Cp, and this is this equation also known as the Fourier-Biot equation. So this is the final equation, and as you can see, this equation represents the steady state condition, okay, with heat generation, and this equation is commonly known as the Poisson's equation. Okay, when we remove this part, heat generation part, and we simply consider the steady state without any heat generation, this equation transforms into Laplace equation. So this equation is transformed into Laplace equation, and when we consider this part of the equation, which represents the unsteady part, okay, because the time dependence of heat this heat transfer. So this equation is also known as the diffusion equation. Okay, even though it has no heat generation, but it shows the heat transfer rate which is dependent on time. Okay, so the heat transfer which is dependent on time is also known as the transient heat conduction. So this is the case of transient heat conduction with no heat generation. Okay, so this equation is known as the diffusion equation. And as we can see, rectangular coordinates, as we can see from the general equation that we have earlier derived, this is the steady state condition with heat generation. This is the one-dimensional steady state that we have. This actually whole equation represents the one-dimensional heat transfer. Okay, in our earlier derivation, we actually did not consider these two direction, x direction and y direction and z direction. Okay, we only considered only x direction. So the one-dimensional heat conduction equations can be derived from the from this three-dimensional general heat conduction equation. So this is the summary of final equation, summary of the equations that we have derived. As you can see that we are writing here only in terms of one-dimensional conduction equation, This is the for the plane wall one dimensional conduction equation. For plane wall, this is two dimensional this is the is for the cylindrical cylindrical coordinate system, and this is for the spherical coordinate system. And this actually is the case of uh, uh, constant thermal conductivity. If you remember only this part, then remembering the three-dimensional steady state equation or three-dimensional general heat conduction equation will be easier. And these are the some of the review question for you, and you can take this as a homework that you try to derive one-dimensional heat conduction equation in Cartesian coordinate system. These are the references. Most of the PPT is prepared using Sengel, Yunus Sengel, but you can but I have also referred to these two books. These are one of those two famous books. So thank you for this class.